Okay. Okay. Perfect. So let's go to continuing. Do you remember what was the last exercise we was seen last day?
I think it was with the cannibals.
Cannibals missionary. Okay. Probably we started with a complicated exercise. Let me 1 second to find this exercise. Missionary here. Okay. Let's go to remember what we did here. Okay, let's go to make a review of this exercise. We are trying to resolve state problems. That the idea is represent one the situation of take a picture of this problem or game and try to give inside the state the structure. Try to put the minimum information we need to draw this extent of the game, or to make this picture. In the case of missionary and cannibals, we decided to use the state here, this representation. Missionary to the left and cannibal to the left will be enough with only this information, and the place where the boat is will be enough to represent the state of the game, the situation or this picture of the game. So how we can get the missionary to the right? It's only 3 minus missionary to the left, because we know we have 3 missionary and 3 cannibals. Okay, this is the representation. This very important part is probably one of the most creative part of this state problem, is to define the state with the minimum information as possible. Then we have to think about movements. Movements are always same structure. Is I don't know here. More over here. It's same structure. First, the name of the predicates have to be always the same. And then we have movement name. That's the name of the movement. It's a way to know what we have to do with this name. Next part is state before the movement, and what happened after. What is the situation after this movement? State after. This is the idea always. It's always the same. Is the name of this movement. What is the situation before? What is the picture of the game before this movement? And what is the picture of this game after this movement? So, and now, for example, we need to describe or to implement, to create 10 movements for the problem of the missionary and cannibals. Is move one missionary to the left and to the right, move one cannibal, move two missionaire, move two cannibals, or move one and one, because the boat only can maximum can move two people, only maximum two, and the boat cannot be empty. You need almost one person in this boat to make the movement. It's not possible to move the boat. The boat is empty. Okay, perfect. We started with this definition of movements, and we first approach. We started with the most easy approach. Is like write 10 different movements. That will be the most easy the first idea. But we saw that it will be possible to make that more easy. Instead of write 10 movements, write only 2 and change the name of the movement and put something like that. Move missionaire and cannibals, and define the movement, and then here write all the different options. I can move 1 1, 2 0, 0 2, 1 0, 0 1. That means 1 missionaire and 1 cannibal, 2 missionaire, 2 cannibals, 1 missionaire and 1 cannibal. That's left and right here. That means wherever direction that each of these move will be 2 different. It's from the left to the right and from the right to the left. So with this idea, we can do that more easy. Okay, here this implementation is okay. We have to move. Let's go to move a number of missionaries, a number of cannibals to the left. What is the state before this movement? The state will be the missionary to the left, any number, I don't know what is the number, but it's this variable. I can put here whatever number from 0 to 3, and a number of cannibals to the right. What is the situation after? If I move, remember this is the missionary to the left. If I move to the left, that means I am adding the number. This is the reason why here we have missionary plus m. And here we check the number have to be greater than 0, but probably we can remove that because we are going to check if the state is valid or not. But it's good to leave here. It's like, okay, to move, I need to have people, have to be greater than 0 and less than 3. This is some restriction to this movement. And the same happened with the cannibals. I'm adding people to the left, and this is only to check that it's possible to move. Okay, same happened with the right, movement to the right, but in this way, and on this case, if I move to the right, what happened is I am deleting people, subtracting people in the left. This is the reason why here we subtract the number of m to the missionary to the left, because we are changing from the left to the right. So we subtract the number here. Any question about that? This is two movements are clear, or you have any question?
Sorry, I don't have a question, but your audio quality is really bad, like sometimes.
I'm so sorry for that, because I am connecting today with my mobile phone. In theory, I have a maximum signal, Wi-Fi signal, but I don't know what happened. Now, the song is better or not? Yeah?
Yes, now it's better. Like sometimes it's really good, and then
It starts to be worse. Okay, sorry for that. Sorry for that. I have no way to detect that. If you have to tell me. Okay? Tell me if I have to repeat something, or if you have any question. Any question? Is clear or not? I think probably this exercise will be a little bit complicated for the first one, but the song is good now. The song is good now. You can't hear me or not? Yeah?
Yeah.
Okay. After these movements, next part is create the path to the solution. The path to the solution, we apply induction, and the path have this description. We have an initial state of the path, a final state, and a list of visited states. It is very important, this list of visited, because otherwise Prolog will enter in a loop and trying to do always the same things, like move one missioner and back, move one missioner and back, something like that. Trying to repeat the states. It's very important to have this list of visited states, because this is the only way to obtain the solution. Otherwise, Prolog will enter in an infinite loop and never finish. Okay, and at the end the path. And when that is true, the path will unify with the list, sorry for this, list of movements to go from initial state to final state. So we started with one state, one situation, and we want to reach one final state. And we are going to make a sequence of movements to pass or to change from initial state to final state. Okay, how we create this path? Using induction. The idea is, first, think about the most simple case for this path. Most simple case for this path will be if initial state and final state are the same. And for that, we put here the same variable, initial and initial. That means initial state and final state are the same. That means, okay, we finish. We are in the state we are looking for. In this case, what is the list of movements we have to do? What movement we need if we are in the final state? We don't have to do any movement, so the list is empty. In this case, we have an empty list here. And visited, is finish the job. The only task visitor have to do is try to avoid this infinite loop. So here doesn't matter what is the visited state. We have to visit and to reach the final state. Doesn't matter because we are in the final point. So we finish this path, and we have no option to reach this loop, infinite loop. So here doesn't matter. We leave this variable like this. Okay, for the induction, we try to move from the initial state to any state. We call this state temporal or intermediate, auxiliary, whatever. And from this auxiliary state, we will try to find a path to the end. So it is first make a movement from the initial state here, from the initial state to the auxiliary, and then we check that is a valid state. That is valid because this is not and not. We have double negation here, and at the end that means that is valid state, the auxiliary, and this state is not already visited, because it's very important to check that any new state, they are not in the list of visited states. And finally, we made a path from auxiliary to final state. And we have to do with visited is to put the visited before. Sorry, the auxiliary before, because we have to update the list of visited states. Okay. I don't know, is that is too hard or not? What do you think? Tell me some idea. Tell me something. It's too much? Luca, what do you think?
But did you do something on Wednesday? Because it's slightly different than the exercise that we did on Monday. So since I don't follow the Wednesday lesson, I didn't know if
we didn't have the lesson on Wednesday. It's only what we did on Monday. Or not? Probably I take the I don't know. Probably we finish here, no? Okay. Okay. Okay, probably if we stay with we did that until this point, no? Until here.
A little bit later.
Not valid.
Until here.
Until here.
Yep.
Yeah. It's more or less the same. The only change is this simplification of this movement. Two movements instead right 10 movements, but that will be good too. But it's exactly the same. This more simple case and this recursion or induction with this movement. Yes, it's a little bit different. Yeah. Which is not valid and it's not invisited. The rest is the same. It's the same. Yeah. This is probably this is the exercise we did the last year, not this year. Okay, but it's the same idea, only writing two movements instead to write 10. Okay, let's go to make a break. 5 minutes. Okay, let's go to continue, because probably would be a good idea to start with another more simple exercise. Probably let's go to start from 0. We have 1 hour more, and let's go to resolve this exercise later. I prefer to start from the beginning a new exercise, more simple. Okay, and after that we will finish the other one. Okay, so 5 minutes break, and back in 5 minutes. Okay, see you. Hear me? Okay, let's go to continue. I'm checking. There one error here in this code. I intend to resolve that, what's happening, but sometimes it will be a little bit complicated. I have to check, because there's something that is not that something wrong here in this code we did last day. Because we did here in a different way. I don't know, is something related to driver state. If there's some mistake here, it will not be possible to reach the solution. So in this case, if we try to check this code, at the end it said it's false. I am executing step by step. That is possible to do that. If you want to check, for example, you have this code. I'm gonna send you in the chat this program. If you want to do with me, for example, the missioner notes. This is the code we did last day. Okay, and as Lucas said, it's not exactly the same I was explaining before. This is a different code. I'm gonna send you that too. If you want to see the difference, it's similar, but we changed the movement. And this missioner.pl. Now you have here the two options, the two versions of this code. Let me check if this works, because there's something wrong in the code of we did last day. Give me 1 second. And we are trying to do another exercise from 0. Or if you have any question, probably will be better. Try to resolve one exercise from 0. Let me see if that works. Like, okay, there are no errors here. And to get the solution, I need the path. I'm gonna write here the solution. The solution will be the path. Yeah. The solution will be 0 in the left, sorry, 0 missioner Now 0, 0 in the left, and the final state is 3, 3. It doesn't matter. Okay, let's go to check the solution. Okay, here we have a solution. Implementation works, but there's something in the other implementation we did last day that doesn't work. I have to check what is happening there. Okay. I'm going to show you a way to try to find this type of errors. It's like the name is this graphical debugger. Will be the first time you listen this term of debugger. That means it's try to find an error in one program. And usually people in computer science have tools to try to resolve this type of problems. I'm going to show you how to do that in Prolog. We have to write here graphic user interface tracer. That will open this graphic user. It's like a new window where we can see what is happening inside the code step by step. And after that is say, okay, graphical front end will be used for some subsequent tracing. And next, we have to say trace. That means, okay, execute step by step next goal. And the goal will be load this initialize nodes. And now we got solution. We have to try to execute step by step the solution. See what happens. Solution P. Now Prolog open this new window here, where you can see the code and here the variables, and we here this button, so you can run step by step and see what is happening with this program. At the beginning, we will call to the state with the initial state 0, 0, right? And this is the information with the variables. Visited is empty list, initial state is this state, final state is it. And we can execute step by step, clicking here in this button. And now probably are going to check from top to bottom all these movements, all the movements we write. First one, I'm trying to move one missionaire. And here we can see what happened with the variables. The new state is 0, 0, 1. Next part is check if this state is valid or not. 0, 1 is valid or not. That means there are 2 missionaire and 3. So this is not valid. This is a not valid state. So it's not possible to do this movement. That's 4. The same with the next one. And at the end, 1, 1 is this is a valid state. So check is not invisited. Okay, good. So the first movement will be this one. Move 1 and 1. And so on here, you can see step by step what is the the evolution of the variables or evolution of the program, and that can help you to try to find some errors. Sometimes it will be easy to find, sometimes not. It depends on the problem. In this case, you see you need to advance many steps to try to find what is the problem. So in this case, it will be not easy. Here's one. Basically, this is the state, the list of movements. In this case, we need a lot of steps to see what happened here. Okay. Okay. I'm going to try to do that. Anytime I'm going to review this code for the next day. And now we have almost an hour. We are going to resolve a more simple exercise from zero. I'm going to explain again from the beginning how to resolve this type of problems. Okay. Let me, in this week, I'm going to check this code and see what happened, what is happening. You have the two options. I send the two code, the code of last year, where you have this solution that is working, is good. And this one that I have to check what is happening here. Okay, probably there are some error. If you are making a mistake only in one arithmetic operation, probably it's not possible to reach the final state. In this case, they say there are no solution. And when we ask at the end, they say that is false. Probably we make some mistake, and it's time to check. If you want, you can try to check by yourself. Try to check the code, but sometimes it will be difficult. You have to review all the movements, check that everything is okay. Probably we can remove these things here. Don't worry about that. So we'll check and tell you what is the problem. But these type of problems will be difficult because they are not syntax error. There's some error probably in the arithmetic operation, but you have to check one by one and try to find where is the error. Okay. So next day I will tell you the solution. Okay. So another exercise now, more simple, and it's the problem that appear in this film. That's the name is hard drive 2 problem. I don't know if you remember this film you see before. Hard drive 3 or 3. Hard drive 3. Okay, this problem. The problem of these gallons. They are a bomb that is have a time to exploit, and they have two these actors in this situation have two garages with one of 5 gallons and another one with 3, and the idea is to get exactly 4 gallons or liters is the same problem, but exactly 4 here in the garage of 5. This is what we need, and the movements will be to fill the garage or the bottle, to empty, and to pass from one bottle to the other bottle, the content. So this is the problem. We want to obtain exactly 4 liters in the graph of 5, and we are going to define the movements, the state to obtain the solution. Okay, This is the you have hard drive problem. This is the situation. We have one graph of 3, another one would be, for example, 5, another one with 3. And the first part of the problem is to define the state. Then we have to put inside the parentheses what I have to put inside to represent the situation. What do you think? What information I have to put here inside? Liters in 5 and liters in 3, for example. 2 variables that will give me the number of liters of this graph of 5 and this graph of 3. So what will be the initial state? The first state will be this representation. What will be the initial state? What is the initial situation of the game, of this problem?
Both are empty, I guess.
Sorry?
Both are empty, so 0.
0, 0. The final state. What we want. What's the final state?
So in the first one, I guess we need the 4, and in
4.
the other one, doesn't really matter.
Whatever. Doesn't matter. That is our state and initial state and final state. Perfect. Part of the solution is define movement. Fill 5 liters. I can fill liters. I can empty 5. I drop the water. We'll drop. Which movements can do? Put 3 liters in 5 liters. Or 5 liters in 3. The content of the graph of 3 in 5 or the content of 5 in 3. You think there are more movements or not?
We can also put whatever content of one of the two container in the other, not necessarily 5 liters or 3 liters.
Yeah, when I say 3 liters, no, that doesn't mean
Okay.
exactly 3. That means the content of the graph of 3 to the graph of 5. Whatever the content will be, 1 will be whatever. Okay, that means they put 3 if you want. The graph of 5 liters. 5. It's not because 3 liters is the content of the graph. Okay. So this is all the possible movements. There are no more movements. Let's go to implement this movement. The movement, so let's say, is always have the same name move and the name field L5. That is the name. What is the state before and the state after? What is the state before? Here, here we will have L5 and L3. That means 2 variables with the contents of this bottle, whatever the content. I don't know what is the amount of water. We'll have, this is a number with a number that I represent the number of liters of the graph of 5. And what will be the state after field L5?
5 and L3.
5 and L3. Perfect. L3, we don't modify L3, so it's exactly the same. And here, I can put whatever, because doesn't matter what is the content of the 5. At the end, this graph will be will have exactly 5. Next movement, let's call field L3. State before. So before L5, L3. What is the state after? If we fill the L3 graph, similar to the previous one, is like that it remains exactly the same, and here it will exactly 3. So that means what is the content here? Here at the end we will have 3. Okay. Can you try to do the next exercise, the next movement? I'm gonna give you 5 minutes to try to do the other 4 movements by yourself, and let's try to resolve what is the solution. So I'm gonna disconnect for some minutes and try to complete this movement with the same format, like the name with non-capital letter. That means that this is a constant, not a variable. A state before and a state after the movement. Okay, if you want, I can share this file to you. It's for example, oh, sorry. Okay, I'm gonna send you this file. You can continue with this code. Oh, sorry. Here. Give me 1 second. I don't know how to program. Save as. Here. Okay, now you have the code. Sorry for the. I try to finish these movements by yourself. Okay, I see your result in some minutes. 5, a little bit more. Okay, it's very. This exercise is more easy, less movements, more easy to resolve. Okay, so take your some 5, probably a little bit more. I will reconnect to see what is the result. Okay, see you then.
I don't know if it is right.
Yes, sorry, I was. Okay.
Well, okay. The dropping is easy. It's just like the feeling with the final state equal to 0, right?
Okay.
As for the putting, let's say I create this variable here, L2,
yeah,
which has to be less than a how you say it has to be limited to the how much space is left in each container, right?
Okay. Yeah, if the total amount is like L2, what is the value of L2?
We don't know. It depends. Okay. It depends on the state.
Okay, you have to do some changes to do what you are trying to do. Is first before the comma, the last comma here, yeah, you have to put 2 points.
Right.
Yeah, okay, and that's perfect. And it's not possible to do what you did. You're trying to do L5 plus L2. You have to use the operator is.
Okay, right.
Like not here. You have to put outside in the right side. Here you have to put some variable. For example, L2 will be this variable. L2 is whatever you want. I don't know exactly. You are trying to put L3 in L5, so will be L3 plus L5, no? I don't know exactly what you are trying to do.
Well, it isn't said that we can power all the contents of one container in the other. Maybe just a fraction of it.
Yeah. You have two options. If you are trying to put the content of L3 in L5, will happen two different things. First thing, the most simple is the content in L3 plus L5 are less or equal than 5. In this case, it's like you have a bottle of 3, you are going to put the content in the 5. You have two options. The content of the 2 bottles is less or equal than 5.
Okay.
In this case, you have to see what happened. What happened if the content of L3 and L5 is less or equal than 5? That happens is L3 will be 0, it's totally empty, and L5 will have L3 plus L5.
Okay.
L52, for example, if L52 or another variable. So you need L52 if you want.
L52?
See, yes, it's the new content of L5. Not put, for example, it will be the underscore if you want.
Yeah.
Underscore that is L52 is L3 plus L5. Okay, and if L52 is less or equal, is not, you don't use here is, just only remove is. Okay, is than 5, and then what happened? You can here put a dot and remove the last part you right there. Okay, what happened in this case when L52 is L5? But all the content is possible to put in a bottle of L5.
It would be this part would be L5 plus L3, as we said.
Yeah,
right?
Yeah, that's it. That is L52.
Sorry?
Use the variable.
L52. Okay.
Yeah, it's not possible to. It's
And
not
here
possible.
would be 0.
Yeah, exactly. It's not possible to put here the arithmetic operation. You have to put outside with this is operator.
With this, okay.
You have to write the other case. You have another case. What happens if you can copy and paste? You can copy this line and paste.
Yeah.
Yeah, and write what happened is great. Is greater than 5. What happened is greater than 5.
If it is greater than 5, here I will have 5.
Yeah.
And here I will have the difference. So
yeah, the difference.
5.
But don't write there.
Yeah. I have to create another variable.
Yeah, another variable, exactly in the right side, like
so,
L32 exactly, and you have to say, okay, L32 is what?
So if I have I don't know if it is major than 5.
Think about is you can extend the bottle of 5. Think about you can extend the content. You can have the bottom more bigger. What happened is the total amount is L3 plus L5, and the amount that is over the
the sum minus 5.
Yeah.
Right.
Yeah.
Okay, so we will have
5 L5.
No.
It's true. Is L52 minus 5.
L52 minus 5.
Yeah, it's the same, but you have, you have the Yeah.
Okay.
Okay. And you have to do exactly the same with the other. Yeah. You have to put the other two options, like but in this case it's put L5 in L3. You have to change.
So just a moment. So here I should have 0, and here I should have L3 2.
Yeah. And
Right?
you have to L3 2.
Yeah.
That's it. Okay, and a space. Leave a space. Leave a space. Write a space between the name of the variable and the operator. Will be sometimes Prolog will leave a blank space. There. Okay, perfect. Better. And the same in the other case. Like, what happened if r greater than 3?
Here I have to define again. Well, here I will have only 3.
Yeah.
So again,
Or 5, perfect. Greater than 3. And L5 2. 3. Now 3. Perfect. I think it's okay. I think it's perfect. Okay, that's right. You need an. Okay, perfect. I think that is okay. Okay, now let's go to implement next step. Thank you, Luca. Thank you so much.
sorry.
Thank you so much. Let's go to implement the last part. It's the path. Okay. We have the movement. Can you share your code to the other classmate can use it? Can you share, Luca, your code in the chat? Perfect. I'm gonna paste here. I want to remove that. Okay. Next step is the definition of the path. Path definition. Now let's go to apply induction as we did before. Path from initial state. Doesn't matter here about visited, and the movement is empty. That is more or less always the same. If I am in the initial state and final state the same, doesn't matter about what is the content about visited because we finish. and the movement is empty. And now path from initial state to final state, visited state. What we're going to do now is try to find a movement name from initial state to a temporal or auxiliary state. Move. And after we have to check that not member out in visited is very important. They're not already visited this state, and then path from where. Help me to finish this line. From where to where? Remember here, what we're going to do is try to find initial, we'll try to find the final state. This is the path we are looking for. And the length, and what we're going to do is try to find a movement from initial to out, and after that, a path for out find this movement, and then a path with n-1. And here we have the induction. This path has one movement less than the full path. So, what we are looking for here, we have the movement.
We looking for the path from the auxiliary step to the
Auxiliary to final. What happened with visited?
it's the last step we did is the head, and the tail is visited. No,
The head is? What's the head?
the move we just did, the path we just went through.
But visited is a list of a state.
Exactly, yeah.
What is a state? The new state. Now, here we visited a new state. What is a new state we visited? Sorry, Alexander, probably you said, but I didn't understand you. What is the new state?
The auxiliary state.
Exactly. We have a new state, it's auxiliary. We have to add to visited. We have to update. And if that is true, here we have a path. Can you describe what is inside this path? What do we have inside this path? Remember that path is a list of movements, of named movements. Can you tell me what is inside the path? Here
Yeah, the movement
is the list of movements to go from where to where.
Well, right now in this step from the initial to the temporary.
No, here in line 53, this path is from where to from where? From here to here. So this is the list of names of movements to go from out to final. And what is different, or what is the difference between this path, is n-1 path, to this one? What I have to do to this path to make that path through? What is the difference? can tell me what is the difference here between this path from auxiliary to find and the path is here, but the path is from initial to find.
There's one element more.
One element more, but what is the element? What do you have to add here to this path to make that path?
Movement name.
Exactly. Exactly. Name. Everyone see that or not? Something very simple. It's only one element that less. It's very simple change, but it's very important to do in a good way because it's only very simple change. It's only one element less, but we have to do this modification in a good way. Everyone see that or not? Or just some question, or you don't see this change? It's okay. Laura, did you see that or not?
Yes.
Yes? Okay. And the rest of the people, Elsa, please tell me, what do you think? Elsa o Adriana, Oliva.
It's mostly okay.
It's mostly okay. I don't know what that means. It's mostly okay. It sounds not so good. It's like yeah, we're always doing the same. It's very simple change between the n-1 and the n. We only have to pay attention about what is the difference between this path, that is the solution of the n-1, and this path. And in this case, the only thing we have to put is this movement here before. Okay, let's go to check if that works or not. Let's go to open Prolog and load this file. I'm going to share this before if you want to check by yourself. Okay, let's go to check. Hard problem. Okay, we have an error in line 39, singleton variable L3. Let's go to see L3. Is L3 true, right? 39. Line 39 is the L3 true, no? Is L3 true? It's okay. I think so. Now we want a path from the state. What is the initial state? 0, 0. And the state is exactly for whatever. Basically at the beginning. Empty list, no state at the beginning. I can say. And I want the path. Solution. Here we have a solution. I can check if that works. Let me do one thing here. Let's go to try to find the most little one. Like length of this path is L. Yes. Then it's 10. We're going to try to see if there are a path with 9. Yes. There are paths with 9. Let's go to see if there are paths with 8. Yes. 7. Yes. And with 6. That would be the 5. Is this a path with 5? No. We have a path with 6. That probably is the shorter one. The most little path. Let's go to check if that works. At the beginning, we fill L5. We have 5 liters in graph 5. After that, we put L3 in L5. That means we have 2 liters in L5 and 3 liters in L3. Because we put the content, the 5 liters, and try to put in the bottle of 3. That means the bottle of 3 is full, and in L5 remains 2 liters. Drop L3. The 3 liters go out, and now we put L5 in L3. That means now in L3 we have exactly 2 liters. After that, fill L5, and at the end put L5 in L3. That means in L3 we had 2 liters, and we put another one, and now we have 4 liters exactly in the graph of 5. We have sadly 4 liters in the graph of 5. So we have a good solution for this problem. Question? It's okay, you are happy? Are you happy? Now we have deactivate this bomb. We are alive, thanks to Prolog. Okay, this is a very simple way to resolve. You can resolve in this way many different type of problems. Only describing the state, think about what is the initial state of the problem, what are the movements, like to describe the different movements with this simple structure like name of the movement, a state before, and a state after. You describe all the movements, and after that the path. And the path is always the same. Initial state, in multiple cases, initial state, doesn't matter about visited, and the list of movements is empty because we are already in the final state what we want. And then the other case, trying to move to anywhere to auxiliary space or state, and from there try to find a path from auxiliary to final state. And that's all, always the same, and you can resolve many different problems. Okay? It's okay, Luca. It's okay. Nice. Any question? No questions? It's okay. Okay. So this week, time to find your exercise you want to resolve, or a state problem if you find another one, or any of this list of 99 problems. Okay. Perfect. If you don't have more questions, no?
Maybe I have one question for the Sudoku. So
Okay.
yeah, maybe I want to do it if I have enough time. So yeah, do you have some extra information for that?
Yeah, you can see. Yeah, I'm going to send you the, or you can go to the page of Marcus Triska. He have a good solution for that. Will be nice if you try to understand how this code works. Probably
Okay.
only see, understand how this code works will be a very good exercise for you. If you want to resolve this Sudoku, you can resolve many complex Sudokus with this code of Marcus. I can help you to try to explain the things you don't understand there. Okay. More questions? So nice. So have a nice week. See you next day.
See you. Bye.
Okay.
Thank you, you too.
Bye.
You
You're
Bye-bye.
too.
welcome.
Bye.
Bye.